Okay, today we're going to learn about the derivative of inverse functions or inverses of a function. Remember when you were in Algebra 2 that the first thing that you did when you wanted to find an inverse function was to swap x and y. That means if your original function had the point 1, 2, then the inverse function would have the opposite point switching, so it's 2, 1. For us in calculus, when the original function has a slope of dy over dx, the inverse function will do exactly the same thing. It has exactly the opposite point, 2, 1, but then the derivative gets flipped over. So it becomes dx dy. So the wording that you'll see in your book, which unfortunately they have basically one example of an inverse function other than inverse trig. But they do have the formula somewhere around the inverse trig section of the book, but really don't use it very well after that. Okay, so the formula says that the derivative of the inverse function of f is equal to the reciprocal, so flipping over the slope of the original function derivative at y. So what they're telling us is that the x and y get switched. So the inverse x is really the original function y, and we do the reciprocal of the slope. Okay, so generally what that would mean is if I had an original function, to do the inverse I would have to swap x and y and anti-derive or derive implicitly, and then use the opposite value. So for example, if I were to have f of x equals x squared for the x greater than or equal to 0 part, we're talking about only the right-hand side of that parabola. So this is x squared for the x greater than or equal to 0 portion. So if we're talking about the inverse function at 4, that really means that y equals 4. So on the original graph of x squared, the y value is 4 when the x value is 2. So if x is 2, the y value is 4 on the original function. So if we were to take the derivative of x squared, we would get 2x. The derivative of x squared at x is 2, because we have the x value is 2 for this function, would be 2 times 2 would be 4. So if we want to do the inverse function, technically we swap x and y. We only choose the first quadrant portion. So we have x equals y squared, which technically is the graph here. And we're only choosing the first quadrant part because we said x had to be greater than 0 and y had to be greater than 0. So that's the restriction initially. If the initial one was in the first quadrant, the inverse will be as well, because all the points are swapped, but they're all still positive. Okay, that means that if we do the derivative implicitly, the derivative of x is 1. The derivative of y squared is 2y dy dx. We can solve for dy dx by dividing by 2y. That means that on the original function, 4 has to equal y squared. So we're going here. This is the inverse function. And the inverse function at x is 4 means 4 equals y squared, which means y has to be plus or minus root 2, and we're choosing y equals positive 2 because we're in the first quadrant. So the derivative of the inverse function substitutes y equal to 2 into this equation, and we get 1/4. So notice what happens. The original point is 2, 4. The inverse point is 4, 2. The original slope is 4. The inverse point slope is the reciprocal. So we are not going to do the long way. Mostly because we would not be able to solve this equation necessarily by hand if we wanted to do the inverse function. So not every function, the inverse, is easily solvable. So instead we will do the original at the original point and flip. Okay, so for the first example, I'm going to use my calculator, actually for the first two examples. Because I want to know how to make my calculator do all the work for me if possible. So if we want the derivative of the inverse at x equals 1, that really means that y equals 1 on the original. So I'm going to put y1 is the original graph, x cubed minus 4x squared plus 7x minus 1. Y2 is going to be 1, so that I intersect these and get the x value. And this will be the original x value, not the inverse value. So I'm going to go into my calculator. For the y equals, I'm going to type in x cubed minus 4x squared plus 7x minus 1 and 1. So I want to know where the original function equals 1. So I'm going to graph. I'm going to find this intersection. Now what's nice about my calculator is that I'm going to write down x equals 0.349, but I don't want that rounded value. I need my final answer to be precise, so I'm just going to put a dot, dot, dot to remind myself where that was. Now the process is, we're going to take the derivative of the original function. I can make my calculator do that. Alpha f2 derivative of y1, so at x dx y1, at the x value that was just found. Since your calculator just solved that 0.349, that's actually still the value that's in your calculator. I can prove it. I'll press x. So x is 0.3493708. So notice I have the full value, not the rounded off value. So I took the derivative of the original function at the value that was stored into x and got 4.5712144417. Now what I can then do, I'm going to go up and clear this one out just so you can see. Okay, I did this derivative. Now I can do the reciprocal of that, 1 divided by the previous answer. So I can either go up on this calculator and grab that, and it'll give it to me, or I can do 1 divided by second minus sign, or actually the negative sign for answer. And either way, it'll take the previous line's answer and put it there for you. Okay, so what I have here is I found where the original curve, so the original curve has the 0.349, etc., comma 1. I found the slope of the original curve at that value was 4.571 dot, 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 dot. Again, I don't want this rounded off. I want the full value, so I get a final answer here that'll be precise to 3 decimals. So then that means that the inverse function derivative at 1 is 0.219. So the inverse point is 1 comma 0.349, because it has the opposite point as the original function, and it has the reciprocal of the slope. Okay, so let's go over and do that again. I'm going to put f of x equals e to the x plus natural log of x into my y1. Since this is the inverse at 3, that really means that my y value needs to equal 3. So I'm going to use my calculator to get the function e to the x plus natural log of x and 3. I'm going to graph to see where these intersect. So I'm going to graph first, find the intersection, Okay, notice what's happening. I want to show you this one because if I try to initially graph this, the default for your calculator is to try to start at the origin at 0, 0. But the natural log function does not exist there. So notice I don't actually have a value. You actually have to be on the curve for it to work. So I need to move over a little. So as long as I move over onto the curve and actually have points, I can just press enter, enter, enter. So I found the intersection. I'm now going to quit. Notice that I have the stored value of x, that's correct. I'm then going to do the derivative with respect to x of the original y1 function at the stored value of x. And then I'm going to flip that over. Another way, by the way, of flipping, besides doing 1 divided by, I can raise the previous answer. So if I just set x to the -1, that actually means reciprocal, because it's like x, it's like a variable to -1, so it's 1 over x. So 1 over this, and I have my answer. So notation-wise, this means that the inverse function derivative at 3 is 0.259. So geometrically, the original function has the point 1.074, 3 and a slope of 3.859. The inverse function has the point 3, 1.074, and the reciprocal. Because we're swapping x and y, it means we're flipping over the derivative. So the original dy dx gets flipped over, so it's dx dy. So this was our final answer. Okay, so without a calculator, if y equals e to the x squared, we're going to find the derivative of the inverse at x is 1, which really means y equals 1 on the original function. So we want 1 equal to e to the x squared. Technically, we natural log both sides to get 0 equals x squared, but you should know that anything to the 0 power is 1. So that means x equals 0. So the original point on the original graph is x equals 0, y equals 1. So that means that the inverse function has the point 1, 0. Now the original derivative is e to the x squared times the derivative of x squared, which is 2x. So the original derivative at 0 is 0, because we're multiplying by 0. That means that the inverse derivative, so f inverse derivative at 1 has to be the reciprocal, which means the derivative does not exist. So we have a horizontal and a vertical line. But the answer is D and E. Okay, so again, without our calculator, if we want the derivative of the inverse function at 9, that really means that y equals 9 on the original. So for the original graph, 9 equals x cubed plus 1. 8 equals x cubed, so x equals 2. The original derivative is 3x squared. The original derivative at 2 is substituting 2 into the derivative, going to give us 12. That means that the inverse function has the point x is 9, y is 2. So it's the opposite. So notice on the original function it was 2, 9. The inverse function is 9, 2. So that means that the inverse has a derivative at 9 equal to 1/12. Okay, so again, if we're doing the inverse at 5, that really means the original function has y equal to 5. So 5 equals x cubed plus 5x minus 1. And just by noticing, actually, not by any particular solving, I would notice that if I put 1 in for x, I would end up with 1, 5, and -1. So I know that x would have to equal 1 to get y to equal 5. So the original curve, if x is 1, y is 5. Or you could have set that up on your calculator. So the derivative of the original function is 3x squared plus 5. So the derivative of the original function at 1 is 3 plus 5, so 8. That means that the inverse function has the point x is 5, y is 1, because we flip. And the inverse derivative at 5 is 1/8. So we're switching the x and y, switching the x and y, so flipping over the slope. Okay, so inverse at x equals pi really means that pi has to equal x plus sine x. So if I let x equal pi, I would have pi plus sine pi, which is 0. So it actually comes out as pi. That does not, however, mean that the slopes are the same. It means the point is the same. You can have lots of different slopes go through the same point. Okay, so the original point is pi. The original derivative is 1 plus cosine x. So the original derivative at pi is 1 plus cosine pi, which is 1 plus -1, so 0. That means that the inverse function, switching the x and y, we still have pi and pi, but the derivative of the inverse at pi is 1 over 0, and the derivative does not exist. Since derivatives are limits, they do not exist. It's not really undefined. So again, we ended up, sometimes we have a horizontal and a vertical. Okay, so we're not doing calculators on this part because I'm giving you the point. So if I'm giving you the original point, the original point 1, 2, the original derivative, 3x squared plus 2. The original derivative at 1 is going to be 3 plus 2, so 5. That means that the inverse has the point 2, 1. So the derivative of the inverse at 2 is the reciprocal 1/5. So again, giving you the original point. So if the original point is 1, 4, then the inverse point is 4, 1. The original derivative is 10x to the 4th plus 3x squared. The original derivative at 1 is going to be 13 because it'll be 10 plus 3. So the inverse derivative, f inverse derivative at 4 is 1 over 13. Again, at x equals 1/2, well, that should be a good sign right away. If you try to put x equal to 1/2 into this equation, you're going to get sine of 1/2, which does not, well, it makes sense, but it's not something you would be able to do without a calculator. So you've got to remember that that is y equal to 1/2 on the original. So on the original, we have 1/2 equal to sine x. Notice our interval is from -pi/2 to pi/2. So y equals 1/2 means that x has to equal pi/6. So the original point is pi/6, 1/2. That means that the inverse point is 1/2, pi/6. The original derivative is cosine of x. So the derivative at pi/6 is cosine pi/6, which is root 3/2. That means that the inverse function has a derivative add a half equal to 2 over root 3. And they very rarely simplify that on a multiple choice. They don't really care if there's a radical on the bottom, as long as the radical isn't square root of 36. Now that would definitely be simplified. But if it's the square root of a prime number, they're going to leave that. Okay, so for the next one, we're finding the derivative. The inverse function at 1 means that the original 1 equals cosine of 2x. So between negative pi over 2 and pi over 2, we have to know where cosine equals 1. So that means that the angle, 2x, has to equal 0, which means x has to be 0. So the original point is x equals 0, y equals 1. The original derivative, due to the chain rule, isn't just negative sine, it's negative 2 sine of 2x. So that has to do with the chain rule. So the inverse function has the point 1 comma 0. So the inverse slope is going to be the reciprocal of the other slope. So the original slope at 0 is going to be 0, because the derivative at 0 has sine of 0, which is 0. That means that the inverse derivative, so the inverse derivative at 1 is 1 over 0. So D and E. Okay, again, if we're looking for the inverse function at x is 6, if I set 6 equal to the original function, you could do with your calculator usually, but on this one we're doing x greater than 0. I notice right away if x equals 2, I'm going to get 6, because 2 cubed is 8, and 4 over 2 is 2 would be 6. So you could do that with your calculator, or if you notice that they have a particular solution, you could do it that way. So this one could go either way. I would allow the calculator on this one, because only one of the solutions is rational. Okay, so now the original function has the point 26. The original derivative is 3x squared plus 4x to the negative 2. Okay, so this is x to the negative 1, so that comes down as positive 4x to the negative 2. So the derivative at 2 is 3 times 4, which is 12, plus 4 over 4, which is 1, so 13. So the inverse of that switches the point, so it becomes 6, 2. So the inverse derivative at 6 is the reciprocal 1 over 13. Okay, 6 is definitely something you should expect to see by hand. So the inverse is 2. That means that the inverse point has x equal to 2. So that means that y equals 2 on the original function. So if I square both sides, I get 4. If I add 4 to both sides, I get x equals 8. So the original point is x equal to 8, y equal to 2. The inverse point is x equal to 2, y equal to 8. So the original derivative uses the chain rule, 1/2 x minus 4 to the negative half times the derivative of the inside. So the original derivative at x is 8 is 1 over 2 square root of 8 minus 4. 1 over 2 square root of 4, which is 1 over 4. So that means the inverse at 2 has a derivative. So watch my notation. That got a little crazy. The inverse derivative at 2 is positive 4, so we just reciprocal. Okay, so on here we have the inverse function has x equal to 1, which means the original function has to have a y equal to 1. So we set 1 equal to x cubed and get that x has to equal 1. So on each curve we have the point 1, 1. The original derivative is 3x squared. The original derivative at the point 1, 1 is 3. So the inverse derivative at 1 is 1/3. Okay, I would allow the calculator on this one. I'm going to set up that's if the inverse function has the point x is 6, then the original function has to have the point y is 6. So 6 equals 3x plus the sine of pi x when x is 2. Because we would have 6 plus sine of 2 pi, which is 0. So that means I have the point 2/6 on the original, so 6/2 on the inverse. So the derivative of the original is 3 plus, because of the chain rule, the derivative of sine is cosine pi x, but times the derivative of the inside puts a pi in there. So f prime at 2 is 3 plus pi cosine of 2 pi. Well, cosine of 2 pi is 1, so the derivative is actually just 3 plus pi. So the inverse derivative at 6 is the reciprocal. Make sure you do the reciprocal of the whole thing, not each piece. That's not the same. Okay, so you have to make sure that it's the entire thing flipped all at one time. Okay, so if we're restricting ourselves to the first quadrant, the inverse at x equals 16. So if the inverse function has the point 16 as x, then the original function has to have 16 as the y value. So 16 equals x squared, means x equals plus or minus 4. Since we're in the first quadrant, we're going to choose x equal to 4. So our original point is 4/16. The inverse point is 16/4. The original derivative is 2x. The original derivative at 4 is 8. So that means that the inverse derivative at 16 is 1/8. So the equation of the tangent line for the inverse uses the inverse point and inverse slope. So y minus 4 equals 1/8 x minus 16. For the next one, the inverse has x equal to 4. So that means that the original function has to have y equal to 4. So if 4 equals x cubed plus x squared plus x plus 1, I notice right away that x would have to equal 1. So the original point 1/4 on the inverse is 4/1. The original derivative is 3x squared plus 2x plus 1. The derivative at 1 is going to be 6. That means that the inverse derivative at 4 is 1/6. So for writing the equation of the tangent line to the inverse, we use the inverse point and inverse slope. So y minus 1 equals 1/6 x minus 4. Okay, now the AP exam uses these charts most commonly when they ask you for an inverse derivative situation on a free response. So if f to the negative 1 is actually notation for the inverse function of f, not the reciprocal, find the derivative of f inverse at x equals negative 1. So remember, if the inverse has x equal to negative 1, that means the original has to have y equal to negative 1. So we're going to look at the chart first and figure out where y equals negative 1. Y equals negative 1 if x is 0. So x is 0, y is negative 1. The slope of the original is 4. So the original has the point 0, negative 1, and f prime of 0 is 4. So the inverse function has the point -1, 0, and the derivative of the inverse at -1, because remember we're switching the x and y, so they should not be the same typically, equals 1/4. So the answer for part A is 1/4. Now using what we did in part A, we're going to write the equation for the tangent line to the inverse at -1. So that means we're going to use the inverse point, so y minus 0, and the inverse slope, 1/4 x plus 1. Okay, for the next question, again, we're going to do the derivative of the inverse function. So we're looking for g prime of 4, which really means we need the inverse derivative at 4. So if the inverse has the point x is 4, the original has to have the point with y equal to 4. So 4 equals x cubed plus x squared plus x plus 1. I can notice right away, and they did put this on the 9 calculator question one year, that x would have to be 1. So they're expecting you to have a little number sense to notice that 1 plus 1 plus 1 plus 1 would be 4. So the inverse has the y value as 1, but the original has the x value as 1. So the derivative of the original is 3x squared plus 2x plus 1. The derivative of the original at 1 is going to be 6. So the inverse derivative at 4 is 1/6. Okay, this is also a very common question on the AP exam for inverse questions. They only usually put a couple on there. Sometimes it shows up on the free response, not that frequently, maybe once every 9 years or so, but they do show up a couple of times each year on the multiple choice. So notice the wording here again is that g is the inverse of f, and we're looking for g prime at -4. So that really means that the inverse has the point -4 is x. So we need to figure out the original if -4 is y. So if the original has to have the -4 as the y value, I have to choose f of 9 equal to -4. So since f of 9 equals -4, 9 is the x value. That means for the original, we're using x equal to 9, not x equal to 4. So that means that f prime of 9 is equal to 3 given to us. So that means the inverse point has -4 as the x, 9 as the y, and the inverse derivative at, -4, which is g prime at -4, is going to be the reciprocal of 3, so 1/3. Again, the table of value questions are very common for this type. So if we want the inverse at 4, that means the inverse function has x as 4, but the original has to have the y value as 4. So if we're looking at the original g function information, if the y value has to be 4, that's going to occur across this line. So the original has the point x is -2, y is 4, and g prime of -2 is 2. That means the inverse function switches, x is 4, y is -2, and then the g inverse has a derivative at 4 equal to 1/2. So when we're writing the equation of the line tangent to the inverse, that means we need to use the inverse information. So y plus 2 equals 1/2 x minus 4. E. Now this next question is one of the ones that people find hardest because once you see an inverse idea, you forget that you have inverse other information. We only memorize the derivative of inverse sine, inverse cosine, inverse tangent. Inverse cosecant we would do by solving instead. So if I cosecant both sides, cosecant of y equals x squared. I would do this derivative implicitly. The derivative of cosecant is very, very much like the derivative of secant. The derivative of secant, remember, is secant x tangent x. A derivative of cosecant, because it starts with a c, is going to be negative, but then it's negative cosecant cotangent. And because we have the y term implicit, we have to do dy dx. And that's equal to 2x. So then dy dx, when we solve over, is 2x divided by negative cosecant y cotangent y. But that means we typically see the negative sign written on the top or in the front of the fraction. And then what was a fraction on the bottom, think about what we have here. We really have 1 over cosecant and 1 over cotangent. So the reciprocal of cosecant is sine. And the reciprocal of cotangent, 1 over cotangent, is actually tangent. So the correct answer for this would be B. Okay, so for the next one, we have calculators allowed. So we're going to put, this value says that the inverse has the point x is 2. So the original, my handwriting is getting worse and worse. The original has to have the point with y equal to 2. So we're going to put y1 and y2 into our calculators. I'm going to clear that out and type in x cubed minus 2x squared plus 5x minus 1 and 2. So I'm going to graph to find the intersection. Okay, so I'm going to take this over so we have it written there. So that means that the original function had the point 0.737, comma 2. So the inverse function has the point 2, comma 0.737. So remember, I don't want to round that value off. I'm going to use the calculator to do the derivative of y1 at x equal to x. And remember, that's the stored value for x. So I'm going to quit. And we can test that our stored value of x is correct. And then do the derivative with respect to x of the original function at the stored value of x. And then we reciprocal that, flip it over. So that means that the original slope was 3.682, and the reciprocal slope, so the inverse derivative at 2 is 0.272. Okay, so calculators are allowed, but they're not always required. So for 17, if I know that this is saying that the inverse function has x as negative 3, that the original has to have y as negative 3, I can set negative 3 equal to the cube root of 3x minus 5. So if I cube both sides, negative 27 equals 3x minus 5. So negative 22 equals 3x, and x is negative 22 over 3. So if I do the derivative, do a different color, y prime is 1/3 3x minus 5. Make some space, guys. So the inverse point is negative 3 and negative 22 over 3. The original is negative 22 over 3 comma 3. So the derivative of the original is 1/3 3x minus 5 to the negative 2/3 times 3 because of the chain rule. So that'll cancel, and we just have 1 over 3x minus 5 to the 2/3. So the original derivative at negative 22 over 3 is going to be 1 over negative 27 to the 2/3, which is 1 over 9. So the inverse derivative at negative 3 is 9 over 1. Okay, for the next two, you're definitely going to want to use your calculator. So remember, the inverse has x equal to 3. So the original has to have y equal to 3. So I'm going to clear this out. I'm going to type everything, if I can, with the new calculator exactly the way it looks on my paper. So I have sine of x squared. Okay, remember this square needs to be outside the parentheses. If it's inside the parentheses, it's squaring the x. If it's outside, it's squaring the whole function. I'm going to set that equal to 3. Find the intersection. Okay, 4.309. So 4.309 comma 3 flips to be 3 and 4.309 on the other graph. So I'm going to make my calculator do everything when I have a calculator question. So I'm going to clear this out. I'm going to double check. If you ever bump your graph, so I found the intersection. If I bump over it all, then the x value that I'm on is the x value that it knows. So I have to be careful not to bump the graph. So after I find the intersection, it's probably in my best interest to make sure when I quit that I have the correct value stored. Then I'm going to do the derivative with respect to x of the original function at the stored value of x. So the original slope is 1.223. So the inverse function derivative at 3 is equal to the reciprocal .818. Okay, so we're going to repeat the process for the next equation. So remember, the inverse has x is 3. The original has the y value, it's 3. So if we type in x, e to the cosine x, and 3, graph, and find the intersection. Does surprisingly happen only once. So we're going to calculate the intersection. Okay, 4.335. So really the reason that I'm writing this down is in case they ask me to write the tangent line, but also so I can make sure when I quit that I have the correct value of x stored. Okay, so I'm going to do the derivative of the y1 at the stored value of x, and then I'm going to flip it because we swapped the x and y. So the original derivative at 4.335 is approximately 3.481, and the inverse derivative at 3 is approximately 0.2 0.87. Okay. So on here, we're looking for the derivative of the inverse to f of x. So they don't always use the notation. Sometimes they spell it out. So you have to read very carefully. At x is 6. So that again means the inverse has the x as 6, but the original has the y value as 6. So we're going to intersect those on the calculator. So our y1 is x plus 3 sine x. And the y value is 6. We find the intersection. It's 6.212. So the original curve has 6.212 as the x, and the y value is 6, so the inverse switches. So I'm going to quit. Make sure my correct x is still stored. Do the derivative of the y1 at the stored value of x, and flip that. So the original derivative at 6.212 is approximately 3.992. And the inverse derivative at 6 is approximately 0.250. Remember, you have to do 3 decimal places. So either truncate or round. In this case, it both rounds down, but you cannot say 0.25. If you write down 0.25, it means the answer was exactly 0.25 and you didn't have to round. The extra 0 implies that you know the exact value out to that place and that there were other values out there that you actually rounded. Okay, so it has to be 3 decimals or precise, and 0.25 is not 3 decimals, nor is it precise. Okay, so now finding the derivative again. Definitely with your calculator, because look at your derivative choices. Okay, so we're going to use this. If we want the derivative of x inverse at x is 2, that means that the inverse graph has x is 2. So the original graph has to have the y value as 2. So we're going to do x cubed minus 3x squared minus 2x plus 1, and intersect that with 2. Okay, 3.627. So I'm going to write that down. So I'm going to find the original derivative at 3.627, and the reciprocal of that is going to be the derivative of the inverse at 2. So I'm going to make sure I have the correct stored value of x. Then I'm going to do the derivative with respect to x of y1 at the stored value of x. And I'm going to flip that. So the original function had a derivative at 3.627 of 15.709. And the inverse is the reciprocal, is 0.064. So the last question in the notes. Okay, this is definitely a free response question from 1977. And I was still born before that, so in case you're calculating. Older than that, so that's not right. All right, so on here, determine the value of each of the following. I always have kids every year that read this wrong because it was typed this way. The derivative of f plus g meant the entire f plus g, not the derivative of f and then plus g. Most of the others, people didn't read that, but it's surprisingly enough, I have tons of students who don't even read the first part and just do f plus g at 2, and they don't ever do any of the derivative part at all. Okay, so you got to make sure you're reading correctly. The derivative of f times g. So the first one is really just going to be the derivative of f plus g is f prime plus g prime. Okay, so sum and difference are just normal. So at x equals 2 would mean that we had the value straight across here. F prime at 2 plus g prime at 2. So 6 plus 7 or 13. The derivative of the product, however, is not a regular product. You have to use the product rule. It's f prime g plus g prime f. At x is 2. So we have f prime times regular g plus g prime times regular f. So 6 pi plus 14. The derivative of f divided by g is the quotient rule. It's low d high minus high d low over the square of what's below. And we're doing that at x equals 2. So then we get regular g. Whoa, that's funny. Okay, we get regular g at 2, which is pi, times f prime at 2, which is 6, minus regular f at 2, which is 2, and g prime at 2, which is 7, all over g squared, which is actually pi squared. So I end up with a ton of students that want to cancel this, and it absolutely does not cancel. This is 6 pi minus 14 all over pi squared. If it doesn't factor, then it doesn't cancel. Okay, no factor, no cancel. Okay, so since pi doesn't factor out of the top, you absolutely cannot cancel this out. Nothing simplifies. Now the next part says find h prime of 1. So notice it says determine the value of each of the following. Looking for h prime of 1 if this is the composition function that we have. So h is the composition, not the product. So it's the chain rule. H prime of x is the derivative